Oh. Just had to do that. The evil noise. You know, right before we start, even. Just to filter out the weak. Oops. There we go. Hey everybody. Oh my god. Random amount of large people. Hi. How's it going? I just want to say I'm without audio. Good. Good, you're without audio. Oh my gosh, it's Storm. What type of problem am I doing? I'm working on this dynamics problem. We're doing some angular kinematics. It's fun. There's a lot more math in dynamics because you can define, you know, motion as a vector function. Oh, my voice has changed? Oh, if it's been a while, yeah, my voice is probably pretty different. Yeah, it's been a while since I've streamed early enough for you to catch it. My bad. I wish I could stream at like 2 all the time, but 2 is when my classes end, so but yeah, it's nice to be able to get to do you know, work with paths and vector functions and all that sort of stuff, but we don't really get to do it as much. I mean, like for this class you can see it's like this is a circle, which is kind of sad, but what are you gonna do? You know, what are you gonna do? So last time we were trying to figure out this little proof showing that the acceleration of pin B is of constant magnitude. Now, okay, wait, I was supposed to get my caption thing set up. It's physics? Yeah, it's physics. But it's like math physics, you know? It's much more math. It's like applied math though. But it's not like statics was just physics. You know, that's straight up only physics. I feel like if you're doing algebra, you have to call it physics. You can't call it math. This is like you're doing math. I mean, more so. Okay, let's see. So pin at B is free to slide around the circular rod. We're just gonna do a little review. Circular slot DE. When you write the second derivation with 2 points, it is some physics. Okay, I wish that we didn't do this because I like prime better. That's just me though. Not that it really matters because like we don't actually really do that many functions. Metal pipe, thank you. Killing me instantly. My brain just turned off. Okay, so does the radius change at all? No, the radius doesn't change. So r is constant, which means that equals 0 and r double dot equals 0. So in that case, it's just going to be a constant. This is going to be a constant. Let me like rewrite this. What is going on here? What did I do? Why is this? Get out of here. Get out of here. Get out of here. I don't know why that's there. That's, what is it? 2r theta dot? Nope. I forget. What is it? It is 2r dot theta dot, yeah. Let's see.
Metal pipe sound effect.
Metal pipe sound effect. Now I do weak derivative. Weak derivative. It's a way to solve differential equations with solutions which are not differentiable. No, that sounds awesome. What is that? I'd love to hear about it. Weak derivatives. Is it like some... is it for when you can't have solutions to a differential equation, or Is it when they're like, when they have cusps or something? That's what I remember from what a non-differentiable thing is. Okay, so this is, so 0 minus, so theta dot is, so r times, it's a thing, so r is r times theta dot squared. I changed the color of my pen between streams, whoops. 0, r is constant, but theta dot, so constant rate theta dot, theta dot equals constant, so theta double dot equals 0. So we've got 0 plus r dot is 0, which I thought would be the case, but what is this music that's playing? This is like some goofy, it's called The Juggler. I'm trying to record my code working, but it only works when I'm not recording. It knows. It's like electrons. They behave like a wave or a particle when you're not looking at them. Magnitude of A equals r to r dot squared. Constant is r theta dot constants. Nice, that was simple and easy. Maybe you've seen the transport equation in physics. Then maybe you've seen that a signal seems to be a solution but is not differentiable. Then we give the sense of it is a solution even if we cannot differentiate it. Oh, I don't know if this is what you're talking about, but is it like the step functions? Like these kind of functions? Because these would be non-differentiable, I feel like. Behaving like a wave saves on computational power, don't worry about it. Huh, that's fascinating. So how do you like how do you get something out of this? Do you have to like visually do it and then just be like, oh well, it's not differentiable, but like, just A. B, determine the direction of the acceleration. Okay. Well, I mean, it's just in the R direction, right? Because it's A equals R dot this squared ER. So, in the ER direction. Coding is like Lego but with words. You kind of just smush them together into something resembling a plane, look at it and think, how did I make that? Chicken on screen! Oh my gosh, my chickens. God, I love it. This specific track is such a good song. In the ER direction, I guess, or theta up from x-axis. Just really quickly, x, y. I remember, okay, the funny thing is like, I think I overheard people in my class talking about this problem on Friday. And every time I see Kos, I think I overheard them talking about it and they like did a tangent for some reason. I was like, why would you do a tangent? You know that you have it as a vector. Like it's in this direction. I don't know, this seems like really, wait, let me see. Do they have a, wait, maybe there's a solution for this. Nope, there's no solution. I feel like it has to be in this. What the fuck did I redeem? Oh, chicken on screen. Oh, I forgot I haven't put in the thing that it's what it says. We look if we can find a function which would have the same derivative of this function almost everywhere. To be more clear, we search for a function which lets us verify the formula of integration by parts with your function. Ooh, that's so cool. My handwriting is illegible. I've been told that many times. It's not that illegible. What part of this is illegible? So in the ER direction, or theta up from x-axis, this is pretty clean. I mean, maybe that's pretty clean. Started streaming at exactly 10 p.m. and I have to go at 10 p.m. My bad. It's completely illegible. Well, it sounds like a skill issue. I think it's pretty legible. We've had this discussion before. Now, okay, wait a second. I will say one thing that is illegible. Wait, let me show you. This one you can get on my case about. Where is it? Where is it? It's a Saturday. I got school tomorrow. It's a Sunday. But yeah. Wait, these ones are pretty illegible. Oh, you add a lot of way to use my points. It's cool. Oh, thanks. Wait, where's my... This is pretty illegible. But to be fair, this is a fast lecture. I have 4K points to use. Oh my god, you have so many points. Look at this. I can read this though. These are my mechanics and materials notes. Hi, silly. Mine says, okay, this says, works on all linear / non-linear problems because it's proved by symmetry. Internal force matches. No, internal torque matches. Do not ask how many points I have. It says cross sections stay planar after deform. Vertical slices stay vertical. Cross sections stay circular after deformation. Radial lines stay straight after deformation. I don't know why I wrote taffy with a torque symbol. This is rough. Okay, this one was a little rough. This proof was a little rough. This face. This is like the face I make in all my classes right now. I'm just like grimacing. Okay, that's fine. I think it's just in that direction. I feel like there's no acceleration because I mean it's not speeding up radially and it's not speeding up tangentially. I have 50. I have 57,000. Umbra, what are you gonna use those for? That's so many. That's crazy. Okay, I guess this is just the last. I thought that other problem would take longer. You were in the future for me. Okay, let's see. We got a plane. Love planes. At the bottom of a loop in the vertical plane. So I'm guessing we're using polar though, because we have r dot and r double dot. Oh, you can't even see the side of this. There we go. A plane has a horizontal velocity. Okay, so that's our tangential. V equals 315 miles per hour and is speeding up at a rate of 10. So that's V dot equals 10 feet per second squared. Ew, feet per second and miles per hour? That's kind of cringe. Let's put this into feet per second, I guess. Can I post a GitHub link to the thing I worked nonstop 12 hours on? Yeah, of course. Miles use kilometers. Sorry, we're in America. I'm in America. We are in America. I'm pulling you into America with me. You're coming to America. What is that? 3 times 2580 and then divided by 3600. Okay, that's not too bad. 22.575 feet per second. Okay, let's do this smartly. Okay, the radius of the curvature. Ooh. Okay, we're gonna start in. Did someone say feet? Oh no. The radius of the curvature. We're gonna start in. Me just hitting my face. We're gonna start in. What is it called? Path. Or we're gonna start in intrinsic and then we'll go because we have a little 5. Wait, did I say? It's 5280. Did I actually do that? Did I say 3280? I said 2580, not the right thing. Sorry, gamers. 5280. It's a pendulum with an airplane? No, it's okay. No, it's an airplane, like, lifting up. Like, turning up. It's not a pendulum. Thank God, that would be kind of crazy. Okay, 462, that's even nicer. Okay. Alright, we got all our variables up here. The plane is being tracked by radar at point O. What are the recorded values of r dot, okay. So our acceleration will start in path. So that will be v dot e sub r. So that's our radial change, which is going to be 0. Wait. Nope, e sub t comes first in t. God damn it, I was thinking of the other way. Yeah, v dot e sub t, and then we've got v squared over rho of e sub n. So that's our normal. So our v dot, or this is going to equal, I don't know, 462. That's not right, I lied. 10 feet per second squared. Sorry, I can do this. Plus 462 squared over 5280. And then we go feet per second squared. Okay. That's RA in terms of radial type stuff. Not radial, I lied. I don't know why I said that. Intrinsic coordinates. 462 squared divided by 5280. Okay. 10. Nice. So now we're gonna have to convert between this and that. So we could, oh, we know that, do you know the streamer Pen Center? They do math too? Oh, I have not heard of them. Wait, I'm gonna look them up right now because I'm curious. Are they live right now? Am I stealing their thunder? They're probably not getting their thunder stolen. I bet they're bigger. Oh, they are live right now. Oh shit. Ooh. Ooh. The guy that answers math questions. I love that. I love that for them. Brian. That's so real. Brian. Okay. I'll have to check out their stuff. Where's my shit at? There we go. Whoops. He answers problems of people in Discord or some sort of forum. Ooh, that's cool. I am like not good enough to do that all the time. I can do it sometimes. I usually just answer my own questions, but you know, no. If people come in here with questions, then sorry, my brain just stopped working. Damien, I'm gonna be eating dinner before we have a Sunday to Monday crisis. Sunday to Monday crisis, as in like it's just a regular occurrence. I don't want to drive to work. I gave him an integral, he died on it. It's okay, I died on your integrals too. I mean, I could still try and do one of your integrals. I'm not as good as I used to be. I am also having a Sunday to Monday crisis because, if you guys didn't know, I go to a school in California, which is a CSU school, and all our professors are striking for a week. So I gave him a complex integral. Oh god, have I done those? I might have done those. I don't know. I'm trying to remember how I did this. So I think I can say that like the acceleration equals this, but I think we need to project these vectors onto the other. No, we need to make so we have acceleration as a vector, and we need to project it onto each one of these. Yeah, I think so. Should we try it? We did it without projecting in my other class. This requires me to... Okay, let's see. The integral was e to the negative it divided by... Oh, Jesus Christ. I've already got to the point where I can't do it. Cos squared t. Oh, I gotta make this bigger. No, sorry, cos h squared. I don't even know that. Oh, divide all of it by cos h? Oh, I see. Okay, slightly. How do you even start that? From negative infinity to infinity. Oh my god. My engineer brain looks at this and I go, oh, what? I don't even remember how you could start this. Do you have to, like... The result is beautiful. I don't even remember what cosine, hyperbolic, cosine, how... I don't think I ever learned how to integrate hyperbolic cosine. It seems like it's a tricky little guy. It seems like a little trick of a guy, to be honest. If I remember well, the result is pi over sine, hyperbolic sine, t pi over 2. Ooh, that is beautiful. Sorry, let me grab my... So we were doing this projection thing in class. I just need to remember how I did it. You don't need to put infinities on integrals? Yeah, you don't. You're right. Silly head. Okay, well, what if you wanted it to be fucking, you know, from, I don't know, it's been a while since I've done integrals. I'm used to, when it's like infinity, I'm used to being like, oh, it's a, you know, it's an infinite integral, and then you plug in infinity, you do the limit to infinity, and then you get something else, you know? You know? It's been a while. It's been a while, guys. Most of the, I'm not even gonna lie, like, out of all the math stuff that I use, well, it's kind of absurd, because, like, okay, take a class like mechanics of materials. You can do mechanics of materials on, like, for example, like a beam, right? You can simplify many things to be a beam. But, like, let's say you have, you know, like, a weird thing that looks like this, right? You can do the same setup, but you can use an integral, right? And you know, we could be doing this because we know integral. But for some reason, my professor's like, no, you guys, you don't need to do that. We're only gonna do the one where you don't have to integrate it ever because it's just a constant function. And it's like, I would be using integrals a lot more, but so many of my classes are like, fuck it, we ball, we don't need it. But then, you know, so the most of the stuff I end up using is like linear algebra, because we just have a lot of systems floating around of equations for various things, or something like this, like projection, not really only linear algebra, but, you know, vector stuff. Let's see, so VR equals, this is when I was saying, oh, we should just do this. VR, okay, well, this is for V, not for A, but I think, wait, sorry, I'm my brain. VR. We have V. Wish I could show you guys what I'm looking at. I mean, I could. Oh, wait, no, we're doing the same thing. Acceleration. We split it up into. Oh. Wait, what? What? Wait, do I have it? Yeah, that's how I feel. Wait, let me take a picture of this. Beautiful emoji, thank you. I know, it's like me when I lie. Where did my phone go? What's happening? What's happening to me? Everything's falling apart at my fingertips. Okay, well, I guess I can't take a picture of this. Pino! The King Pino. I know, he's here and he's big. Okay, let me just draw this. So we did a problem that was like, So it was this sort of linkage thing, and there was a point that was moving here, and we had a tangential velocity this way and a normal velocity this way and a tangential velocity this way, and we were trying to find it in terms of this one, which is our other ER based off of this point down here, which I just realized you couldn't see. It's that point there. And then the E theta to this one. So this and this. And this is 60. So the way that we did it was how did we do this? We had... Wait, maybe that's just V. I was not doing a very good... I'll go ahead and say hello to Penn Center. I'll come back after. Okay. Have a nice time. Where? What is happening? V... Why did I like comma ET? Oh. There's no V dot. That doesn't... My brain is hurting. Look, trying to decipher this. I was trying to remember if I was drawing V or if I was drawing the components of V. I think this is V. I don't know. My brain hurts good. Sorry. Anyway, that's not really useful for what we're doing. I should probably just draw it out. Let's draw it out. Let me stop lollygagging around. Okay. That's A. And then there's B. Wait, no, it's not. There's no A and B. This is just one problem. Okay, so we have a plane, we have a point, or it is a plane. It's going on this point. So right here, this is the V. This is V. So we're trying to find R dot, R double dot, theta dot, and theta double dot. So we got V. In terms of the plane's being tracked by the radar at O. So that's R down there. So this is our R. Probably figure out, like, you know. Let's see, 24, 18, 30, 60, 90 triangle. Let's see, 2400 squared plus 1800 squared. God, giant number. It should be like 30 maybe. Yeah, 3000. So this is 3000. I mean, it's not always going to be 3000, but at this second it is 3000. So it's our VT. And then we have I guess I should probably say this is AT is in this, or ET. And then we have, let's just say the radius of curvature is way out there. Or it's kind of, sorry, it's kind of like that. So what we want to try and find is R. Okay, those are not 90 degrees. Might be, should be straight up. EN. It's a 90 degree here. And we know that that is, I think it's a 30, 60, 90. And so that's 60. This would be also 90. Means this would be 30. I'm just trying to lay down some groundwork. I mean, I could do with that 60, but I could work with the 32. I think I have to project it onto R, but I'm not exactly sure. Sorry, big stretch and yawn. let's experiment a little. Okay. So, I mean, we can write down our other guiding equation. That would, you know, probably be smart. So the other one we have is this one right here. A double, r double dot minus r theta squared minus r theta dot squared is our ER, and then plus r theta double dot plus 2r dot theta dot. Okay, let me move this over just a little bit. Theta. So if we can find like the magnitudes, essentially if we can find the magnitudes of r, ER, and E theta, then we can find find our r dot and our, so like if we want to find r dot, we can like set this equal, you know, all that good stuff. Okay. I think we just have to project them onto the... I think I'm just being silly. I think I'm just being a silly Billy. Because... Okay, the only thing we might need to do is say that... Yeah, so we do need to find ET and what EN are. So ET in this case is 0 or 1 0 XY. Let me do this. 1 0 XY. And EN is 0 1. Right? Okay, well we just got lucky. That's not always the case. So we know that this vector then is, so like A equals 10, 40.425. So if we want to project that on, so ER equals ER equals, what do we, oh, I mean, I guess I could just straight up put, that's kind of funny. I could just do 24, okay, 24 over 18. Well, what do they both divide by? 6, 4 over 3. And then E theta. I'm just interested to see if this will work. And if this is like easier, because I feel like if I tried to do this, we did it geometrically, but I was like, what if we just project the vectors? Because like, vector projection is not that hard, you know? Okay, so for E theta, we have, what do we have? E theta is at a 90 degree from R to the left of R, always. Which, well, let me just like do my little right hand rule. I guess it would be this way, because R is pointing towards the plane, so it would be this way. Which means that this is 30. You ever see anybody draw a 90 degree symbol this big? We drew it even bigger. What about that? I feel like that's pretty good. That's 30. Alright, so if it's 30, then we can, I mean, we could just say like, oh, we could say, so for 3x you go up, so, okay, 3x over, you're gonna go down 4y, I think. It's the same vector as, it's the same direction as R. Wait, did I get bamboozled? Wait, is this 3, 4? It should be 3, 4, right? Because the 60, no. The 60 is the long side, the 30 is the short side? Yeah. Yes, yes, yes. Yes, they get switched. And then it just points downward, so we know that. So then we're going to say projection of A onto ER equals their dot product. Oh shoot, I didn't normalize it. That is not a unit vector. Okay, let's see. 4 divided by the magnitude, so 4 squared plus 3 squared. See, my toxic trait is, sorry, square root of 4 squared plus 3 squared. Oh, it's 5. Why am I... My toxic trait in engineering is trying to use vectors for things. That I probably shouldn't use vectors for. But I think it's kind of beautiful. 0.6. See, look how beautiful that is, 0.6. And then this one is 0.6. Great, look how much math I don't have to do. Okay, so projection onto ER is going to be just a dot, right? Let's see, projection onto a unit vector. Check myself. Dot product is a projection. Yep, just dotted. Swag. Okay, so 10, 40.45 dot 0.8, 0.6 equals, 10 times 0.8, so 8, plus 40.425 times 0.6. 32.255, so 32.255, nope, 255. And that's in the ER direction. The ER direction is kind of funny. It's like, yeah, we gotta take a hospital. Yeah, we gotta go to hospital. And then we just project the other one too, and that's not too bad either. It's gonna be like flipped. I wonder if this is gonna give. I really hope this gives me the right answer, just because I'm very excited to see if it does. I mean, it should. Like, there's in no world should this not work, you know. But it's always nice to see your own little things you're trying yourself come to fruition. I explain how pipelining works. Let me take a look at that. Let me see if I know what that is. The term does not ring a bell off the top of my head, but, you know. Or E theta. And I think E theta is supposed to be inward, but I'm not entirely sure, so be good to check that. Okay, let me see, pipelining. CS pipelining? HTTP pipelining, the technique of issuing multiple HTTP requests. Ooh, I do not know about that one. This looks interesting. Let's see, so an instruction pipeline has 5 stages. Instruction fetch, decode and register. Huh. Without waiting for one to begin. Or wait, what is it? The output of one element is the input of the next one? Oh. Wait, that's just normal, is it not? You just, like, finish a step, and then you just do the next one. With the output of the just step that you had on the last one. I think? Isn't this kind of just like, what are the little trees that you guys have, like, these things? I mean, we call them, like, routing, sort of. And like you can, you know, go this way or you can go this way. And then you can like wait and like say like, oh, until something else happens, you know, until like D is completed, then like you can do E or something, you know? Is that not this? This might not be that. So it's to process different commands in Linux. So to process different command in Linux, is it better to call pipe fork inside the child process? Two things, I don't know exactly that case. That's the first thing. The second thing is there might be like certain cases where it might be good, but you know, kind of like in all programming, it might be a case by case basis. Let's see. Can pipe fork? Usually each process handles a single command line. Can a child process work? Child process that receives fork can only okay, well that's crazy. When should a child be when should a child be able to use a fork? That is a baby. That is not a computer science. Let's see. Every example of oh wait, this might be something that's useful. Oh, yeah, I think this is like a pretty good way of visualizing it. Let me, here, wait, we'll pop over to the full screen real quick. Browser. Check it out. So, kind of like what I was drawing, like if you fork it to do something over here, so the parent process closed the read side of the pipe. The parent process. Well, so this is the let me think. The parent process would close the read side of the pipe. I think it would. If you need to close it, because this is just doing the reading, and then this would have to say like, oh, I'm done with the reading. FD is a file descriptor? Mm-hmm. Yeah. Because I don't think it could say... Yeah, I think the parent would have to close it. But I mean, it seems like, I don't know. I don't know exactly how the code works with like, if you have to open and what you have to open and close for the... like how to open and close the read and write stuff, you know? Concept is crazy to understand. I think it reminds me sort of like working on GitHub stuff. Where like you're like passing stuff back and forth, you know? Hard to know whether the parent process works first or the child. I think generally the parent works first. But then when you have like your parent and child processes running concurrently, your child might be doing stuff that the parent's not doing. How did I switch my... Huh? OBS? Hello? It's confusing, as people said fork means clone. Well, let's see. Does fork mean clone? Okay, why does... That's really odd. Huh, okay. Weird. It was switching my scenes. Let's see. Is fork cloning? What's this? Fork is a copy of a repository. Oh, that's in GitHub. Yeah. It's forking the same as cloning. That's in Git. Still. Or Linux. Is a fork cloning. The Linux creates a new process by cloning the current running one using the fork system call. Subsequently, execute, or one of its variants, loads a new program image into the newly cloned child process. Okay, wait. This is like an architecture thing. Sorry, we're like doing a read with me. They both run concurrently, yes. The execute cd command is a forking service. It forks off to a child to handle each client. It opens the Linux pipes, passes them in the exit. It's possible to duplicate. What is an event listener? Oh, I actually do know that one. Event listener is basically like you're saying, I'm gonna open sort of not a program. I'm gonna open a state that says I'm going to listen, like I'm going to wait for an event to happen, and then I'm going to do something when that event happens. So it can be like, I'm gonna wait for the user to like click their mouse, right? I'm gonna wait for the user to highlight something. I'm gonna wait for the user to I'm gonna wait for the server to tell me something. So it's sort of like a wait. Parent process also have a wait system call function. I think wait is for a well, at least from what I would assume, wait is for like a specified amount of time, not for a specified. I think it's sort of like you could have like a loop that's waiting. But like I think an event listener just waits like for it to be thrown the thing that it's looking for. Here, maybe this. Fork versus clone versus No, do not sell or share my personal information. The fork, the clone. Wait, this is GitHub still. But it is hard to code it out, right? Well, I mean, I would just look up like Linux event handlers. They just are, I mean, yeah. So it's a framework that enables SR Linux to react to specific system events using logic to define the actions taken in response to the events. So basically you can say like, oh, if your computer crashes, do this, or something. So you just have to, work with whatever framework you have and just like learn about it a little bit, see some examples, and it shouldn't be that bad. The nice thing about coding is like, as long as you can Google stuff, you're probably gonna be fine. Execute VP, let's see. Exec VP Linux. I just typed Linus or execute file. Exec failure functions replaces the current process image with a new process image. Oh. Problem is, if exec VP is in a child process, it always runs. Well, so it seems like exec VP replaces your child with like a different program and then it starts running it, I would assume. Let's see. Behavior of, wait, so what's the difference between these dudes? They all execute files, but how are they different? The functions described are for the front ends of exec VE. Constant arg in I see. So constant character file. Oh, so you can change it to be a path or a file. Heyo, hello. How's it going? Such intense dramatic music for vectors. It takes in a buffer as a first parameter. Okay, well, let me hold you for 1 second. We do have some... Okay, so we know that... What do we know? It has a horizontal velocity and it's speeding up. So it has a Hiya, hi, how's it going? We know that it has some, normal acceleration, and it has some tangential acceleration. So basically nothing is like off the table in terms of solving for things. So how am I gonna do this? How am I gonna do this nicely? Barraging me with, with emotes. I see. Love that the like poor little guy music started at the same time as that. Okay, I'm gonna bring this little friend down here. I can see it a little bit better right next to our other stuff. Okay, so we know that 32.255 equals r dot minus r theta dot squared. So we do have a radius, so r equals 10 feet? Nope, 1 mile, 528 feet. It's midnight and I just got done doing like 5 integrals. Oh my god. Go to bed. What integrals? Okay, I think we might also be able to, smiles evilly. I think we might be able to, scuff this a little bit. Because our horizontal velocity is actually going to be the same as our... Wait, is that true? Wait. Wait, no, not exactly. Oh, because our radius... Oh, they goofed me. I was about to get got. I was gonna say, oh, it's a circle, so it's the same. Our tangential acceleration is the same as our theta direction, but it's not. They almost got me, Chad. Oh god. Okay. Well, we do know that this r is gonna change, but the one up here is this r is not gonna change. So buffer is just like an array. I remember there are string builders only in Java. This is getting into territory of I don't know the exact technical details. We might just need to system of equations this up. I'm not gonna lie. R theta double dot. There's too many equations for this, is the thing. So okay. Well, how many variables do we have? 1, 2. 3, 4. So no, we can't do that, unfortunately. Although, where can we squeeze 2 equations out of? Malloc is required to create a buffer? Oh, I'm not sure about that. Let's see. 1 over x squared plus 1 to the 5 halves. Oh, okay, so it's like x squared plus 1 to the to the negative 5 halves. Ooh, that's good. Do I remember how to do this? Oh god, I don't know. Maybe you could use sub? No, you can't use sub. What am I talking about? How would you do that? Let's see. Trig sub? No. That would suck also. Oh wait, x squared plus 1. Oh, that's sneaky. You know what it might be is this thing, right? Something like that, potentially. That would be sneaky. What is that, like tangent inverse or something? To the 5th? I don't know how I'd integrate that. It's been a long time since I did any integrals like that. Okay, this one is also making me scratch my head and go, hmm. I mean, I guess I could define R. That I should not do that. Okay, that is the idea that went into my brain. Immediately went out. We are not doing that. How did we do it for this one? Oh, we did it with the velocity to find R. Ooh. Can I explain the L'Hopital rule on limit? Okay, sure. I can take a look. I can attempt. As x goes to 0, of tangent of 3x over 6x minus x squared. I'm going to write it as minus squared minus 6x plus 6x. So for L'Hopital's rule, we take the derivative of both the top and the bottom. Our funny little friend, the derivative, which would be, don't mind me googling tan, secant squared x over 2x plus 6. And then we still don't have, as x goes to 0 for secant squared. Let me see, what does our secant function look like again? In a little while. For that one, as x goes to 0, because as for tangent, we have to make sure that, like, as we're putting things in, we're, you know, that these are both infinity over infinity. Wait a second. Oh no, the chain rule. Oh, you're yeah, okay, well, wait. Times 3. Shh, I'm math. I can do math. I can do math, I swear. Wait, but as x approaches 0, oh, it'd be 0 over 0, right? Is that what we're getting at? Well, let's tan x on x. Yeah, it'd be 0 over 0. Okay. This was secant. As this approaches 0, this would be 0. Or not 0. Any quirky new characters? No, unfortunately, unless I draw this plane as an anthro plane, then I don't think we have any new characters to speak of today. Which I could, easily, but I think I've already drawn an anthro plane on stream for a physics problem. Beginning of my statics class. I see. Well, it's because, like, the other one, there was no guys in it. There were no people in it. It was just, little, little numbers. Unfortunately, we do not always have fun little guys, but we can create them in our hearts. Anyway, let's see. So this is gonna go to, when we do the limit, this will be 6 over... We're actually doing the limit part of this. And then our secant of x is gonna go to 1, I would think. So it would be 3 over 6. Is let's see. If I'm just gonna graph. Have a good night. Have a good night, Storm. Hope you had fun stopping by. Let me graph. Let me graph this on my trusty graphing calculator. X squared plus what do we have? 6x. Nope, that's wrong on my part. Oh wait. Oh, it does look like it goes to 1/2. Yeah, it's like 1/2. Okay, we're chilling. We're chilling, yeah. So you just take the derivative of the top and bottom. Big wins. And don't forget, oh wait, 3x. But that should be okay. That's okay. That's okay. Because it's still 0. Okay. So I found the acceleration, but I also need to find the velocity, actually. Funny story. But I did all this, which is great, but I need to find the velocities before I do this. So I'm just gonna bring this whole thing down, and we'll do that after I find the velocities. I can plug them right in there, so that should be fine right there. Okay, so our velocity in this one is this duder right here. R dot ER, so we need to find, wait, why did I not write normal? Huh? What? What? Gnome! Gnome, my beloved. Oh. You've just been gnome. Okay, I can't do that part. Don't clip that. My voice doesn't work like that anymore. Not as young as I used to be. What was I looking for? I was just trying to find evil mode. Oh, now I'm evil. Evil dynamics. Where's this equation? What am I doing? What's happening? Everything's falling apart. I feel like there's a normal component. Bye, gonna get some sleep now? Yeah, go to bed. I'm glad you got your integrals done. Actually, I'm evil, so I hope you have a bad sleep. I don't mean that. It is just ET, huh? Okay. Okay, sure. But that's great, because I already found ET. Okay, this is great, actually. So V equals -10. Oh, nope. 315, 240. 3 per second. ET. So then we have, if we dot ER, right? Yes, maybe, no? Hey, we need to write the other one. So V equals R, ER, and R dot ER, and then, yeah, so R dot ER plus R dot E theta. Which is awesome. So if we, dot these two, then we can probably define these up there. Let's do that. Right up here. Luckily, they are not too hard to define. But, if we needed to do these with angles, then we could do that too. Now, I hear you saying, Damie, would you do this on a test? And I would say to that, great question. I don't know, because it's going to be a little bit before I have a midterm. May not be the most efficient way. I'm actually interested to see. It's something that I haven't really gotten that much into, but trying to figure out fast ways to do things is always really, really good. Fast ways that are also just applicable to every single thing that you can just kind of like be fast and reliable on. That's sort of what I strive for, at least when I am learning stuff. Okay, so projection of V onto ER equals, we have 462, 0, dotted with 0.8 and 0.6. Oh, well that's nice. It's just this. So, okay, wait, this is our big moment of truth. Is it right? So 369, nice, 0.6. And this is in feet per second. And this equals, actually it just equals R dot. Okay, 369.6. Damn it, 370? Oh wait! It's the same thing. Okay, let's go, gamers, let's go. I multiplied two numbers together. Let's go. Oh my god. Me when I'm like, 370, it's not the same. Okay, she like rounds to, my professor rounds to 3 sig figures. I don't know. It's right, but like, I also feel bad about it. I don't know. Don't look at me. Okay, projection of V onto E theta equals, okay, things are looking promising, but I'm gonna withhold counting my chickens. Okay, times 0.6. 277.2. 0.2 equals R theta dot. So theta dot equals that divided by R, which is 3,000 feet. 0.092. Oh, it's right. It's right. Okay, wait, it's negative? Okay, it says it's negative. I don't know how Oh, okay, I did my theta dot in the wrong direction, gamer. I did it in the wrong direction. It should face the other way. So that would mean that it's positive y, negative x. So positive y, negative x. And that's why we check here. But hey, that's good. We're getting there. What did I get? Negative 0.0924 radians per second. Okay, 2 for 2. Which is giant wins compared to last time. Then we got all this stuff. I really could have drawn the picture a little higher up. Okay, so I'm just gonna do a little swoopy swoop. Okay, and then we just plug in the other stuff. We're chilling. So R equals not 528. This is gonna equal 3000. Theta dot equals negative 0.0924. Yeah, so R double dot equals, let's see. So we have, oops, I just did it again. So 3000 times this squared. That and 32.255 minus 29.69. 29.69. And this would be in feet per second squared. Okay, not correct. Okay. Well. Okay. Where did we go wrong? Okay, wait. No, that one should be correct, because that's the ER. I was gonna say it's like different, because this one will be a different number. Because it's negative 0.6. I'll have to recalculate that one. 10.8 plus that times that. Is that correct? Let's see. Let me just like redo it again. Oh wait, you need to add them, not subtract them. Plus 34.8? Nope, 57.9. That's very different. But I got the first step right, so let's hold the horses. Okay, v dot is 10, and v squared over rho is that. Because that's in our polar from our center. Or sorry, our intrinsic from our center of the big circle. Let's check the numbers real quick. 40 squared divided by... Yeah, 4, so that's correct. And the direction of it is positive in both cases as well. Huh. Let's try this. 8 plus 40.425 times 0. That is very odd that I'm getting this still. If I just square theta up here, and then this times, it's not 5280, it's 3000. Oh? Wait, I might have done something a little different. Oh shit. Why is it always when I just like do what? My calculator is just like hating me. It's just being a hater. 57.86, I just did it again. Apparently I'm very good at dynamics, and I just put numbers in my calculator incorrect. Like, half the time. 87. That's correct. Okay, I'll take it. I'm not complaining. I'm complaining a little bit, but okay, so R equals 3000. That's crazy. I don't know what's up. Oh wait, so we need theta dot in this case. So let's solve for theta dot real quick. So 20, just so okay, I have to redo this one real quick before I do that actually. So negative 6 plus 40.425 times 0.8. 26.34, okay. Important distinction here. There we go. So we're gonna say minus 2, this over R. Okay. So R equals 3000, theta dot equals negative 0.024, and then R dot equals, that was the nice one, right? No, not that nice. 369.6. I don't know why I wrote a number there. Okay, great. Okay, I'm gonna do the 2 R dot theta dot first. So that would be, I'll take the full value, why not? Oh. Times theta dot. It's 2. Okay, 64 something. Then we have 6 minus this, and this divided by 3000. Negative 0.0139. No, this is incorrect. Okay, time to check the calculator first, because apparently, I should probably also, yeah, so 3. Oh wait, theta is negative, so it would be adding them. The addition strikes again. Bro, why are signs like the hardest thing ever? Yep, that's correct. Okay, I need to like keep track of signs better for sure. 0.0315 radians per second squared. And that's it. We did it. We did it, and it wasn't even that bad. And by wasn't even that bad, I mean that it was pretty bad, but we got through it. It only took like how many streams was I doing this? 3? 6 hours? No, okay, sorry, only 5 hours. To be fair, I got a lot of them quicker than I actually thought I got them, because I kept thinking I got them wrong, which, you know, that's always something you gotta just check your calculator, check your whatevers. Okay, let me, because I might do electrical engineering. Oh, it's so nice to just finally be done with this one. God, I was really working on that one for a long time. I'm gonna check out relative motion. Now, we haven't learned relative motion. Okay, wait, no, we have learned, okay. Oh, chat, okay. This is what makes me kind of insane. Okay, so like okay, I can do some of these because they're conceptual. Here's an explanation. I can't get over this. It's like just crazy to me. I mean, this is correct, but like the way that so there was an example of a boat in water, okay? It was saying like, okay, the boat can move 6 knots in still water. Okay, so this is still water. And then it said that what actually happened when the boat was moving from here to here, or it was like, I think it was here to here, kind of. What actually happened was the boat's speed, I don't know, it traveled like 200 miles in like nautical miles in, I don't know, like 50 minutes, or no, it wasn't, it was like 2 hours, I don't know. Whatever, what have you. And you're supposed to like do it as like vectors. So you're supposed to say like, okay, what, because this is the boat with a current going against it. So you're trying to find the speed of the water, like pushing against the boat. So like that's the wrong kind of current. Current equals what? Current equals what? Current equals what? And she was like, okay guys, what is the speed of the boat what is the speed of the boat? And we were like, 6 knots. She was like, no, it's not the speed of the boat. We were like, what? I couldn't go back. It took She kept asking. She was like, "Okay, no, guys. Like, what's the speed of the boat? Like, you don't like what's the speed of the boat?" And we were like, "6 knots," because it was in still water. But like, it's sort of a vector thing where like you have, if this is your reference point, if this is like your reference point of real life, right? This is like your boat velocity, right, or something with the current. And then we do know the boat's true speed, which is like from another reference point to this point. And then this is the speed of the current. But it was like the most crazy way of describing it ever. It's like, this is the most confusing possible example you could have used. Because like, this is like kind of, this vector is like what's happening in real life. This one is like the boat itself. Or this could be the boat itself. It just kind of depends on the problem. Like, we're trying to find out, like, in this situation, you know, we don't know this one or we don't know this one. But it was, oh my god, it messed my brain up so bad. Okay, let's try and take a stab at these. Just so. Wow, that is the fanciest omega I've ever seen anyone put in a problem set ever. Crazy. Homework 3. Ferris wheel is rotating with a constant angular velocity. So with a constant angular velocity, which means that we have an angular acceleration of 0, right? Because our velocity is not speeding up or slowing down. Which means that the only other velocity that we could possibly have is pointing into the center of the Ferris wheel. That is our like normal or radial acceleration. So kind of a weird question because it could be this one, or this one, depending on, or this one, wherever you, oh wait, point A. Like, depending on where you are, they give us a point. It's up. Only A is normal / radial. Then we draw a little happy face because we're happy that we got it right. Always good to celebrate, even if it's a little victory. Okay, let's see. I'm on the lookout for any ones with fun little guys that I can draw as well. Fortunately, we've not gotten there yet, but let's see. Wait, let me actually take a look. Oh my god, I just saw a child. Okay. I scrolled past. Oh, there's another kid. Okay, there's a kid. We can draw the kid. That'll be fun. Maybe it'll be Slinch. Why are there so many children in these problems? There's 2 children, and I've only gotten to like the 3rd problem. Okay. Okay, a race car travels around the track at a constant speed. Again, so like, let's see, no V tangent. Or no A tangent. Only a norm. Which one will have the largest acceleration? The smallest radius of curvature. We saw in some of those GIFs the other day that when you turn around, it goes like crazy wild and then it gets big again. So A, smallest turn, turn largest. Hello, Speen! Largest acceleration. Absolute win for Speen. These are going suspiciously well. How's it going? It's going well. I'm taking some W's instead of only L's, which is great. I like it when we get some. It's when we get the underdog moment where I have no clue what I'm doing and then it actually works out. It's kind of great. Here's the first child. This one's not Slint. Actually, wait. I could draw. Wait. I thought he had cat. What is this? Does he have cat ears? Oh no, he just has a striped hat. Cursed diagram. This is the cat child. Kind of like the little. I don't know. I feel like every physics diagram is drawn like this. You know, like the cats from The Cat Returns. They're just like walking. Let me see if I can draw a walking cat. This is hard. That's not great. Okay, wait, that's better. Okay, that's okay. Yeah, I'm cool with that. Oh, that's like a scoop. How fast would the carousel have to spin to liquefy the child? I don't know if there have been experiments on how much force it takes to liquefy a child. I think that would be unethical. And the government doesn't let us do that. I mean, we do know how much explosive it takes to blow up a horse, though. But the child, I feel like... Well, I mean, I guess they could do, like, a test dummy or something. This is just... I have to include this space over here for drawings of the problem. That's just legally I have to do that. Let's see, there we go. Shade a little bit better. Okay, anyway, this is gonna be like a 2-second problem that I just drew this cat for. Oh wait, I gotta give him his jacket. His big puffy jacket. Yeah, that's a warm kitty. Aw, little guy. That was worth it. Okay, a child walks across a merry-go-round with constant speed u relative to a. Merry-go-round undergoes fixed axis rotation about its center. Oh boy. Okay, there's a lot going on here. Okay, so here's the child. And they're walking out towards A. That's the velocity. There's fixed axis rotation with a constant angular velocity, so it's going this way. What's the direction of his acceleration? Okay, well, there's no acceleration outward, but there's no... Okay. Hold up. So as we're turning this way, we would have like a velocity going this way. The only one we have is a normal acceleration because our angular acceleration equals 0, and our acceleration tangent. Wait, it's the same thing. Tangent, the tangent acceleration is 0, so the only one we have is internal. So, oh wait, viewed from above, I guess it would be to the right, because we have like just normal acceleration. Let me see, how much force? I'm gonna get like on a list for googling this. How much force does it take to crush? Oh, wait, okay, crush bones. Slightly different. Okay, 4,000 newtons of force. 15 G. Okay. 15 G. If we needed a speed of 15 G. 15 G for more than 60 seconds. Okay, so we'll say 15 G. How fast would it need to spin? Okay, so velocity final has to equal 15 G. Wait, negative G is more deadly. Well, no. Okay, we can't have velocity equaling acceleration. Wait, we just need to get up to speed to... Wait, F equals... Wait, what are we asking? How fast it needs to spin? You'll stroke out and your eyes will rupture. How fast? I feel like for a kid it would probably be less than 15 G. Because I'm assuming that's for a human. Like a adult. Okay, how fast do you need to spin it? Also, delta V equals AT. We can figure out how much time it takes. Oh no, we don't want to do that. I mean, I guess we could say how quickly... I think we need to define... So we have an acceleration we need to hit. Our acceleration is 15 G. Right, so 15 times 9.8. I guess meters per second. We'll do meters per second. We're gonna create a new TOS item by the end of stream. No, this is it's for crash test dummies, so don't worry about it. Don't worry about it. Don't worry about it. Don't worry about it. You need to either say like, oh, in this many rotations or this much time. you know? Like, if we wanted to say, like, 10... Like, to get up to the speed. Do you know what I mean? So, like, if we said 60 seconds... Like, because velocity is all about, like, it's, like, distance over time, right? So, like, if you had them going a very small distance, they would need to be going very fast. But if we did, let's say we give it like a minute, because that's how much you said it needed to be for. Let's say like t equals 60 seconds. So delta v equals at. Delta v would have to be, this is assuming we start at rest. That'd be 15 times 9.8, and then times 60. Okay, that's 8,820 meters per second. Which is pretty large. Wait, is that right? Wait, that might not be... That's quick. Yeah, how many miles an hour is that? Wait, I'm trying to think. 2 meters per second. 1 mile, let's say 8830. Yeah, that's like 19,000 miles an hour. Okay, if we wanted to get it lower, 5 miles per second. Yeah, that would be not great. Wait, I feel like this is wrong though, because if you increase the time it takes, you should have... Oh, no, if we decrease the time. It depends on how much well, okay. There's a couple things. Like F equals ma, right? So this is how much force we would need to create, you know, a mass accelerating. So let's just say like, let's see, average. Not saying that one out loud. 17.92 kilograms times times 15 times 9.8 meters per second squared. Let's see. I mean, you could definitely do it. Like, this is like doable, you know? 2,000. So this is in newtons. So 2.6 newtons. So like 2.6 kilonewtons, which is like, that's like not that much force. But you know, you have to keep in mind that like you'd apply this force, and you'd cause this acceleration, and then you could figure out, you know, how much time, or it depends. If we want to make the velocity lower, like let's say we were, what's a highest velocity we can really create. Okay, no. like, okay, what highest speed your car can go? Okay, let's say 200 miles per hour. In 200 miles per hour, 2 kilometers per hour. That's like okay. 321. Let's say that. We want to say that, and then 15 times 9.8 times t. This would have to be very quick. This would have to be very, very, very quick. Yeah, that's 2 seconds. That's 2 seconds. So you'd have to get it, you'd have to accelerate it, or you'd have to make this so it's possible. If you find a car that does 0 to 200 in 2 seconds, I think you would also be squished. Well, because like I'm just trying to say, like, you know, what would you be using to create the force? Probably a car, or like something that you have. It's not easy. What if I laid a motorcycle on its side? I feel like the motorcycle is not going to go faster than a car. Okay, well, you wouldn't get squished if it was like a motorcycle, you know? So at least you're safe there. I think they can go to 210. It's not that much more than 200 when you're getting up there, that was the thing. You might shave off like 0.1 of a second, or you might add another 0.1 second. Faster acceleration? Okay, well, that gets you closer for sure. I think it would be very hard, is my take. Okay, this is the beginning of the silly billies. Unfortunately, this is probably why nobody's tried it. Well, like, I mean, if you just wanted to put a person in a centrifuge, I think you could like do that fairly easily. You know, you just need a big enough motor. And then if you just have them like, because if you create enough force, right, it's like that's the acceleration. So if you put it on a torque, right, you need like less force for because you can just make your lever arm really far. So like if you had a force of, 10 and you put them 10 out, then that's like 10 times the amount of force. They have pilots do that in the military. Oh yeah, they have lots of people do that. They have astronauts do that too. Okay. This is kind of a weird thing. Boats are weird. Already back to work, sorry for the distraction. No, that's good, it's good. I think that's as far as I can take that thought experiment. I think the answer is it would be hard. Like, I mean, I think like if you were trying to squish something with force, the best way to do, I mean, and like this is kind of just like in general, like designing stuff, if you can, like just put it on the end of a very, very long thing. Like, I don't know if you may not know it, but William Osmond's second channel, he had to have a torque wrench of 500 pounds to torque a bolt, and he only had like a 50-pound torque wrench or something, because like you have to, this is like a very expensive, I don't remember how much it was either 500, like 5,000, whatever, like it's 10 times magnitude, and he was like, I need to make it more, and so he just took a piece of, this is the torque wrench, and he just put a bar on it, and then if you torque that until you get it, then you get that much force. So the best thing to do is just put your force really far out, then you get more force. It's kind of like just humanity's greatest invention. I don't know, the wheel is pretty up there, but like lever arms, saying like I can put more force if I put it farther away, that's pretty great. Like pivot points and stuff, I don't know. That's definitely top 2, if not the top invention in my mind. I don't even know if it's like an invention really. Screws are also pretty great. We would not have a lot of things without screws. Oh yeah, the classic end of the ceiling fan is moving faster than the center. Oh, absolutely. Yeah, that's like kind of the entire idea of a lot of like dynamics problems at this point. It's like, how much acceleration do you get as you go farther out, or closer in? Or it's like a figure skater who like pulls the worst drawing Damie's ever done on stream. A figure skater, right, who like pulls their center of gravity in really close is gonna get to spin faster, that kind of stuff. It's kind of great. Those are some good drawings. Okay. Swag. Shore-based radar indicates that a ferry leads its slip with ferocity. Wow. Velocity. Ferocity. I call velocity everything but velocity, huh? Well, instruments aboard the ferry indicate a speed of that and a heading. Oh god, okay. We have some vectors. We have some great vectors, everybody. Everybody loves a good vector. Okay, a heading of... Right. So the shore-based radar is what is actually happening. So that's our vector that's like here, right? This is like shore. And then we have one that's like, this is the ferry, right? So this is like the ferry. And then we have the river going some other way. This is not really accurate whatsoever to the directions that they're going in, but so this is not a particularly hard problem, but if you set it up correctly, that's what it's about, the setup. And I might do it wrong, who knows? Okay, so v shore equals, let's do this, let's say 18 times, all right, I'm gonna just look at this direction. So it looks like we've got a negative and a negative. So negative cosine 70. Now, do we have negative cosine 70? Is that true? If they're giving us that angle, that would be negative cosine 70 and negative sine 70, yes. Then we've got v boat, I guess, equals 18.4. And it says that it's heading 30 west of south. West of south? Bro, what? Okay, never... Okay. West of south, 30 here? Okay. Why do ship people do that? Okay, so this one we have to flip stuff. That's this way. I mean, it's 60. I'm just gonna say it's 60. Makes my math easier. Cosine 60 here. Well, it doesn't make my math any different at all, actually. It should be the same number, but just depending on 45 degrees northwest from south. I don't... northwest east? That just cancels out. Wait, northwest east? You just get north. Northwest is just north, actually. Wait, north from south. North from south would be crazy. Math problems be like, yeah, I don't... The two that really get me are like the ship problems and the airplane problems, because like we have to read like altimeters, and they're just like, they're like, the big one is like 1,000,000, and then this one is like 150, and then this one is like 1. It's like, okay, I don't need to be a pilot, please. So if we add these up, then we should get what the... No. We say v shore equals v boat plus v river. So v shore, so, okay, we'll just do this. 18. Okay, let me do these out. Am I in degrees? Always a good thing to check. Yes, I'm in degrees. I find myself being in degrees a lot lately, and that's odd after doing math with radians so much. But you just don't really use them as much in the out there. Just, I don't know why. Colloquially, people just know degrees more. You know what gets me because I'm careless and read too quickly? I skip the word not instantly. Find out how many numbers are not divisible by 6 and 8. I just skip not and get the whole thing wrong. Oh my god, I feel that. I'll skip like... That is my biggest thing. And one of my friends like just constantly gets on my case because I would do this all the time. I'll skip something like that, and I did that in chem a lot. I would read it and it would be like, which of these are not soluble in something, and I'd be like, oh yeah, the ones that are soluble, okay, I can do that. It's like, no, please Damie, take the 3 seconds to read the extra word in the problem. Oh my god. Oh, my favorite number, 0.866. Okay, I'm really hoping that I get this right. That would be awesome. I finished like 45 minutes spare and I just turned in because I wanted to do something else. That's so real. I love that for you. It's honestly so swag. Oh wait, I have to do a 18 and 18.4. Oh, I can't just ignore them anymore. Okay, 18.4 times 0.5. Okay, there we go. So 3 equals, what is this? 3.044. Please start saying swag and bring it back. Oh, I do say swag. I say swag a lot. I say swag too much. I like swag. It's just like, oh, you know what? That's swag. No? Fuck, I did that wrong. I said swag to the lady taking my passport photo today. I didn't multiply by... No, wait, I did that right. Oh, I did it right. We're good. We're chilling. Don't listen to me, chat. When I say expletive words, explicit words, expletives. Whew. It's one of those days. I need to get my passport retaken. Wait, is the river going? Okay, we're winning. We're winning on the signs. That's a good sign. Get it? Because signs. My passport is expired and I really need to get it redone because it expires like... I don't have any time to get it redone. Okay, so it is this kind of direction. And the magnitude is, so V river, please be right. It also doesn't want to get my Irish one so I can work in the EU and travel if I can't find a job when I graduate. Yeah, that's awesome. That's swag, if you will. What are you a math major? 2.881. It's not right. Oh, computer science, nice. I almost did CS, and then, you know, maybe I should have done CS. Maybe it would have been more fulfilling for me, but that's okay. Both are fine. I like math, I'm just not very good at it. Which part, like, do you, I don't know, you're probably fine at it. A lot of people are like, a lot of people kind of sell themselves short. I'm just slow, that's okay. If you're slow, but you get the right answer, and you understand the process, that's more important than being a speedster, in my opinion. But, you know, school is... Yeah, so I just do it for fun. I don't think I have to take any more math classes. That's so real. Yeah, school's kind of rough. I feel like... I don't know. I teach a lot of people who have been really given a short end of a stick with school. Oh, wait. Was I in kilometers per hour? Did I just, like, goof it? Oh, I might have goofed it. Oh, no. We're still in kilometers per hour. Huh. School's not kind to people. I always feel bad about that. And that's why I try to foster a better sort of learning environment if I can. Oh, it's because I do cosine and cosine? Oopsies. Oopsies. Okay, clear that. I do cosine and wait, no, it should be cosine and cosine. What am I doing? What am I talking about? That's right. What? Okay, now make it sine. Oh, inverse. There we go. I think that's right. Work as a math tutor for like up to algebra 1 or 2, but learning new shit just takes me a while. Oh, that's awesome. I like tutoring. I think tutoring is like some of the best stuff. you could do, really. Because I think, like, if you're a tutor who can really... It's mostly little kids. It's great, though. I liked tutoring when I tutored the middle schooler I tutored because I could kind of tell them a little bit more, and it made them like understand stuff more instead of just like their teachers. I almost said professors. Ah, yes, the middle school professors. No, it just made them like later. Fuck me. No, delete. No, don't delete that. No, delete this. No, it just made them understand stuff more. They love the lore and tricks, absolutely. Yeah, just put a pie in there. That's not what I wanted to do. Can I insert? Just wanna... calculator! Okay, no, delete that. Okay, insert. I don't know why that happens. That's fine. 3.1. Yes, okay. I just did it wrong. Well, I didn't do it wrong. I just put it in my calculator wrong. Age-old story. 9.7 kilometers per hour, and we have this little doohickey here. Nice. So I'm getting paid to teach like multiplication. No, but that's crazy because like out of all of the things that I have done, right? Like dynamics, statics, differential equations, linear analysis, linear algebra, data analysis, all these things that are supposed to be very, very hard. I could not teach like addition. How do you teach somebody addition? How do you live with like knowing that you are the person who's like fundamentally going to determine how they think about math for like the rest of their life? If you fuck it up, that's crazy. Like I could not do that. The pressure of that. Whereas like if I am teaching a linear algebra class, right, and it's like for engineers or something, and they come to this class and they're like, oh, this class wasn't that good. It's like they are smart enough. They are headstrong enough to tell me that, to understand it, to like make me a better professor, teacher, whatever. But it's like for little kids, it's like I had to get a kid in trouble a few weeks ago because they threw some shit at me and started hitting me. Like that's so hard. How do you teach kids that are that young? That's crazy to me. If I had to deal with that in college, that would be I don't know what I would do. I would just have to give up. I would have to quit, I think. I'd be like, you won actually. You bested me in a duel. It's true, but there are lots of little tricks that you're taught when you're younger that we just don't remember. I know, right? Like that's scary. Like I don't know what I would teach. I don't know how to teach that stuff. Oh my god, this is a crazy problem. Move to the right with a constant deceleration. When a boy standing on the deck, D. Thanks for letting me know that that's the deck. I couldn't tell. With an initial velocity relative to the deck, which is vertical. Oh my god, okay. The ball rises to a maximum height of 8. Oh no. Oh, this is kind of fucked. We're putting stuff together. Okay. So we need to find the initial velocity of the ball. Oh, okay. Oh, is this like... This might be a constraints problem, actually. Oh, I just moved my contact out of my eye. Whoopsies. This might be a constraints problem. I don't know if I can solve this one. Let me see. Let me check the lecture, because we... Okay, yeah, I don't... What? Oh, it's a duffel bag. I thought it was pouring water onto the conveyor belt and we had to figure out the velocity. I was like, bro, this is not fluid dynamics. Okay, I think we might have to do a lecture that is on this. Let's see, Monday, online play activity, Newton's second law. Uh-oh. That seems... Intro to particle MA. I don't know. This might not be it. I feel like we haven't finished this motion though. Relative motion. Maybe I can check through the rest of this. Lecture. Because it seemed like a very short lecture. Oh shit. Okay, maybe it's not. We did finish it. Okay, well, I don't know if I can do this right now. I probably should though. How long is streaming? Oh my god, almost 2 hours? What the hell? Sorry, my brain just turned off. I'm gonna get back to work. Good luck with your studies. Have a nice day. Thanks for hanging out for a little bit. That's great. Great to see you. Okay, I guess I could do. I don't really want to do electrical. Okay, let me give a crack at this one. We'll give a crack at it. So, okay, we need to find the distance d that he has to step forward. So there are gonna be two distances. There's gonna be the distance of. The distance of the boat moving, and the distance that the ball travels. So, okay, what do we know? We know that there is a acceleration. Oh wait, the boat's going backwards. Oh. Okay, so our acceleration, so our velocity is positive, I guess. And our acceleration is negative. And then we have our I'll just say velocity is positive, and then acceleration equals negative 0.3 meters per second squared. Okay, that's pretty much all we know. But, so we know that the ball rises to a maximum height of 8 meters above the release point. That can tell us about our that can tell us about our initial velocity, for sure. So we're gonna have to get an initial velocity of the ball relative to the ball, and then we're gonna have to like change that to be in the reference frame of the ship, I think. So let's say find ball internal velocity, not in the real world. Okay, that one was not readable. Not in the real world. Crazy sentence. Just imagining like this ball with like a unique city in it, an inner world, and there's a velocity in there. It's unreal. Like when Mob Psycho went into his own mind. This is the ball world. We're all just living in it. Anyway, it's a little silly. Okay, so to do this, we know that our acceleration is going to be negative 9.8 meters per second. We don't know how long ball takes, but we do know how high it goes. Delta y equals 8 meters. We're trying to find VO equals what? VF equals 0, because we'll just look at the first half of the thing. The first half of the arc that ball makes. Okay, so we don't have t. Okay, so we should use the third one. So VT minus V, or sorry, V minus VO equals. So we have V squared, so 0 minus VO squared equals 2 times negative 9.8 times 8. Okay, so we'll have VO equals, and we don't have a, oh, we do have, we'll know what this is as a vector also. So 2 times 9.8 times 8. 156.8. Oh my god. Did he throw it that fast? What? Wait a second. How fast is that? 0.8 meters per second to miles per hour? What? Oh wait, it's squared. say he threw it 350 miles an hour? This little boy is a superhero. No, square root. 12.5. Okay, that seems more realistic. 12.52 meters per second. Oh boy. Okay. Like. Okay, that's 27 miles an hour. Wait, how fast do people throw balls? Even little league pitchers throw 60 to 70 miles. Okay, never mind. This is not a very fast throw. Good to know, though. This is an average throw. Just dunking on this child. Needed to know that. Okay, we have relative velocity. Okay. I'm making this face right now. That's the face I'm making, because we need to find the actual velocity, right, of the ball. Well, and this is straight up, so it's 0, 12.52. Oh, so our D is going to equal, well, we might have to do a system of equations. So the reason we get a trajectory at all is because of the movement of the ship. So find, I don't really know how to say this. Find, like, ship speed? Real? Because, I don't know how to, no, okay. We'll have to do a little bit of, yeah, so it seems like we have to get the distance D, and then we can do that with the ship to find out how much our V is with the ship, and then we can, back that out. So we can't find the ship speed real yet, but we know that Vy is Vx is caused by, whoops, oh my god, let's write real. Caused by ship moving. That's the only way we have this arc, right? Because if we have our components of velocity, they throw it straight up. If you just throw a ball straight up, it's not going to go, Okay. So we have an acceleration. We don't have a, oh, I was about to say we don't have a time, but we can get a time. We can get a time. Okay, so we have A, want, I guess, like a delta S, need T, I believe. Or, yeah, we can use the, yeah. Because we know that the display, we can figure it out, We definitely need time, though. So, to get a time, we can do, what do we like? We don't have a delta V, so we'll have to do delta S. So the delta S of that whole thing, we'll do half of it and we'll multiply by 2. I'm gonna get rid of this, because that's just kind of for us. This is gonna be used after. So delta S, or like 1/2, or no, delta S equals 1/2 A T 1/2 squared. Or I guess I could just do this. Actually, no, we gotta do it. We gotta do half, I think. Yeah, because then VO. So delta S, so 2 delta S over, or so 2 times 8 over 16. Nope, 9.8. Don't know why 16 was in my brain. Square root of this equals T 1/2 I'm so sorry. You met the mic demon for the first time. It's my constant curse that I have no idea how to solve. Just happens. That was so funny. No, it's awful. It's evil. It's like I'm gonna kill somebody one day with that. I feel like I'm gonna give somebody a heart attack and then they're gonna die and it's gonna be my fault and I'm gonna be convicted for murder. It's awful. It's the worst sound ever. I don't know how to fix it. You know what? I could. Well, I was gonna say I'm gonna uninstall my mic drivers right now, but then my mic would stop working. I'm gonna uninstall and uninstall them right after stream. It was dark and sick and twisted. Yeah, we're doing an exorcism soon. Now that Clem has debuted, we can actually do the exorcism. But, evil mode. Yeah, that's how I feel. That's how I feel every time that happens. What? Oh yeah, the exorcism? Yeah, don't worry about it. We're gonna do an exorcism. We're gonna plan an exorcism. To exorcise the demons out of my mic, obviously. But I have to, like, solve the issue with my mic before we can exorcise the demons. Just for, you know, logistical reasons. It'll be really fun. It'll be a great time. We're gonna try to get the demons out of my mic. I might need to RMA it, which is unfortunate, but I don't know. I have the box for it. I probably should just RMA it, but then I wouldn't be able to. Then I would have to stream on like a potato mic. Then it's potato mic Damie era for like an indeterminate amount of time, which is also not optimal. Hopefully it doesn't happen again. I'm so sorry. I'm so sorry forever. Oh my god. Oh, it's fucked. It's fucked. It's fucked. It's the worst. It's actually the worst. It's so frustrating because it's like I've tried so many things. I've tried literally everything. You should give my professor an ARG level cryptic puzzle that spans across my many assignments. That would be awesome. Unfortunately, there are 14 sections of dynamics this quarter, which is a class of about 30 people, and there are so imagine that, like, you know, 300 times 4, like 1,200 people, and there are only 4 professors teaching them. So, they don't. My professor also doesn't actually grade each problem individually, and unfortunately, my professor doesn't even grade them. The grader would get an ARG level puzzle. That would be beautiful. I mean, I could still hide it in here. I still have, like, you know, I still have this. Wait, where is he? I still have this guy in here. You'll see that guy. You'll see. Here, I'll draw something. This is the Damie viewer who will die from when they start listening to Damie and then they die from hearing. They're beautiful, and I cannot prevent their death, unfortunately, because of my stupid mic. I should give them some feet. There we go. This is them. They're throwing the ball. As you can see from their large and beautiful ears. He's so ugly? Wait, he's so cute. What are you talking about? He's beautiful. They love listening to a Damie. I'd bully him? You're so evil. Literally, he's just some guy. What would you do? What would you do about that? Slinch better? I don't know, this guy's kind of awesome. This guy's kind of awesome. This guy's on par with the quadratic formula song guy. So like, what is he? He has like a hoodie, I think, and he's like evil like this. He's like, did you undo all my drawing strokes there for a second? This is the man on the street with the parabola in his hand. No. He said, "Sir, can you help me? I don't understand." That's the man on his street with a parabola in his hand. And there's his knife that he stabs into your brain. As the song so goes. This guy is also deep damie lore. I think that was a VOD. I think this was a VOD. I don't think this was a pre-VOD damie era. But I don't know. That song is like me. I still love the idea that like Damie's lore is that he's the guy who died in the quadratic formula song. Like it was just me. And that's why I'm an angel, because I like died and I went to heaven after solving the parabola. It's such a funny lore. Like, oh, I just happen to be a catboy also. That isn't the canonical lore, but that's like, it's like the second canon lore. If I had to pick another canon, it would be this. I hope the grader enjoys these beautiful drawings. I accidentally drew a Homestuck character. I'm so sorry, everybody. Okay. I don't know where I have to go with this. I'm like missing one little piece. Oh, tulip noises make my heart feel so lovely. I think I got a capital on this one. Ew, Homestuck. Sorry. Sometimes I just draw the guys like that, without arms, without thinking about it. A remnant of a bygone time, a bygone period. It's okay, I forgive you. Thank you. Thank you. Thank you. Nodders. Okay, so I think that is all I'm gonna do today. I'm proud of you for overcoming it. It's okay, it wasn't that good. There were parts of it that I wish, like the experience of it was actually transformative in the era of the internet, but there are so many bits about it that just made it bad, which is unfortunate because it really could have been very, very, very good. But it was not, and that, you know, that's just how things are. Anyway, so the dilemma I'm facing is that there's the global strike for Palestine that's going on, and I would like to support that. But the other issue is that one of the reasons why I stream is because it makes me more focused on doing work, and it provides people with, for my VODs and stuff, like a library of problems that I can say, hey, look at this problem, like, this is how I worked through it, this is how I solved it. And so, you know, because of the strike that's going on at my school, for the professors that are currently striking, I have a lot of free time that I could actually, you know, do studying content and stuff. So I've decided to step back from like social medias and all that stuff, except for continuing to do the educational streams. So I'm not gonna be like gaming or anything, but it'll just be doing educational streams. And drawing funny guys still in the corner, because that's education. Yeah, so I don't know. Yes, yeah, my school is part of the faculty strikes. It is very interesting, because I live on campus. So like, it kind of sucks because we, like, you could see it two ways. You could see that, oh, well, you could never break the picket lines because you already live on campus. So you're not breaking the lines because you're not crossing the lines. Or you could see that you're always crossing the picket lines because you're already on campus and you live on campus. So it's pretty hard. It's also weird because we're on the quarter system, so like our classes have started, but other schools haven't because they're on the semester system, so they're striking the first week of their semesters, so it's pretty weird, but you know, I'm assuming none of you are affected by it, but basically professors' wages have been getting frozen for like the past 10 years, and they're asking for raises to like be able to live basically in California with the rents and stuff. and some other stuff like gender neutral bathrooms and better support for like better teaching conditions and a lot of other stuff for student support as well. But yeah, I think one of my professors is still holding classes, but most of mine are striking. So yeah, I will be around. I will probably be streaming if I'm not doing lion dance practice. But yeah, I don't know exactly when, but I will post in the Discord when I'm going live. So like I always do. I will see you guys then. Thanks for hanging out today. We did some dynamics. We did some awesome dynamics. Actually, I think I'm getting it. I'm definitely getting it. There's just one little thing about this thing that I don't know. Yahoo! This was a jolly time. It means a lot to me that you are enjoying it. Thank you so much. The hearts bouncing off my head is so funny to me. All right, I'll see you guys when I see you. Have a nice day. Stay safe. Get some rest. Stay hydrated. Unlike me, I never get hydrated. Okay. Bye. See ya.